Welcome to my presentation regarding an empirical model to estimate the fatigue thresholds of specimens obtained by additive manufacturing and containing process-inherent defects. I would like to acknowledge my co-author, Daniele Rigon, a postdoc student of my research group. We know that materials obtained by additive manufacturing are typically affected by defects like, for example, lack of fusion defects observed in maraging steel specimens shown in the pictures below. After presenting a theoretical background on the fatigue limit estimation of defective materials, I will present a model to estimate rapidly the fatigue thresholds. Typically, the estimation of fatigue thresholds of defective materials is based on two material parameters, that is, the threshold range of the stress intensity factor for long cracks and the plane material fatigue limit. Both these parameters are time-consuming to be obtained with laboratory fatigue tests, and so I will present a model to estimate them rapidly without performing time-consuming fatigue tests. And finally, I will show a comparison between theoretical estimations and experimental results. Let's start with a brief theoretical background. The fatigue threshold of defective metal materials can be presented in the Kitagawa-Takahashi diagram, which reports the fatigue limit versus the size of the defect, measured by the square root of the area. The AKLO model, which is reported with the black line here, connects two extreme criteria. For very small defects, the constant stress criterion equal to the plane material fatigue limit holds true, while for very large defect, the constant stress intensity factor criterion equal to the threshold range of the stress intensity factor of long cracks holds true. In the same diagram, we can report the Murakami model, which is plotted by the blue line here, which has two limiting defect sizes, the critical sizes and the transition size. In this diagram, we have to take care to the shape factor adopted in fracture mechanics studies. However, if we use the SIF equality reported here, we can plot in a single diagram the defects of any geometry and any position, both internal and surface defects, by using this effective size, according to the proposal by Lazzarin and Meneghetti. The diagram on the right-hand side reports the same pieces of information, but in terms of stress intensity factor at threshold. Since the experimental determination of the threshold range of the stress intensity factor for long cracks is very time-consuming, there are models in the literature which attempts to estimate such material properties starting from, for example, the grain size and the ultimate tensile strength or the yield strength of the material. Now, if we look at the AKLO line, we know that there are two material parameters involved, the plane defect-free fatigue limit and the threshold range of the stress intensity factor for long cracks. Now, if we limit our discussion to a load ratio equal to -1, the plane material fatigue limit can be estimated from the Vickers hardness according to this formula reported by Murakami. Regarding the threshold range of the stress intensity factor for long cracks, we set up a model based on the microstructural length parameter and the Vickers hardness, and of course the load ratio. So I will present now the biparametric empirical model based on a microstructural length parameter and the Vickers hardness. The analytical expression of the model is reported here. It is based on two material parameters which are easy to find. That is a microstructural length parameter which has a properly definition and the Vickers hardness. The four constants alpha, beta, gamma and delta are dependent on the load ratio R and can be found by fitting experimental results, as I will show you in a while. Regarding the definition of the microstructural length parameter, we started from definitions from the literature valid for wrought materials, and we extended such definitions to additively manufactured materials. For example, by observing the interaction of long crack path at near threshold condition with the microstructure, for titanium alloy, the microstructural length parameter L is the width of the alpha lamellae. In this slide, you can see the calibrated parameters alpha, beta, gamma and delta for different load ratios. The first line reports the calibration for push-pull tests, the second line for pulsating tension tests, and the third line for tensile tests with a load ratio equal to 0.5. You can see that the exponent beta and delta are positive and negative respectively, which means that the threshold range of the stress intensity factor for long cracks tend to increase with the microstructural length parameter, but tend to decrease with the increase in Vickers hardness. If we compare the experimental threshold for long cracks with the estimated by the empirical model for all three load ratios, we can see that estimations are within plus or minus 20%, which was considered to be fairly good for a rapid estimation of the long crack threshold. Regarding the rapid estimation of the defect-free material fatigue limit for different load ratios, we started from the formula proposed by Murakami, where the plain material fatigue limit can be estimated as 1.6 times the Vickers hardness for load ratio equal to -1. This formula is valid only for metals with hardness less than 400, because for higher values of the Vickers hardness, the plain material fatigue limit is controlled by the defects, but we still consider valid this formula with the meaning that the ideal defect-free fatigue limit is expressed by this formula, not the real plain material fatigue limit found by experiments. Secondly, we use the Goodman-Smith model depending on the mean stress to account for the load ratio. Putting together these pieces of information, we came up with the estimation of the plain material ideal defect-free fatigue limit as a function of the Vickers hardness and the load ratio. Now I would like to show some comparisons between the estimations according to the model I have presented and experimental results. This slide shows typical killer defects found, for example, for Malaysian steel specimens we tested in our laboratory. In the first case, we found a distributed defective area which has a very large extension in the angular direction and a relatively short extension in the radial direction. In this case, the square root of the area can be estimated by the square root of 10 times the depth of defective area in the radial direction. In the second example, we have a defective area with a different aspect ratio, and we could evaluate the square root of the area by the surrounding contour. So, first we can plot the model to estimate the fatigue thresholds starting from push-pull tests are equal to -1, we have the fatigue threshold normalized by the plain material fatigue limit with defect-free versus the effective size of the defect normalized by the Haddad-Smith-Topper lens parameter. So we have the plain material fatigue limit estimated by the Vickers hardness, and we have the long crack threshold estimated by the empirical model based on the two parameters. The theoretical model, according to Astori, Lazzarini, and Meneghetti, is the black line. The experimental results taken from the literature are plotted with red markers and black markers. Black markers are the unbroken specimens after a number of cycles equal to 10 to 7, which typically is the endurance limit where the fatigue limit is evaluated. The red markers represent the broken specimens. So if the theoretical model, the black line, had a perfect correlation with the experimental results, it should separate sharply the black markers by the red markers. That is, it should single out the bound between broken and unbroken specimen, which is the definition of fatigue threshold. The correlation is not perfect. We do not have all black points below and all red points above the black line, but the correlation is fairly good. The same comparison can be done for a load ratio equal to 0.1. We have the plain material fatigue limit estimation according to this formula involving the Vickers hardness and the load ratio. We have the long crack threshold estimated by means of the empirical model. With the black line, we have the model according to Astori, Lazzarini, and Meneghetti. And finally, we can plot the experimental data. In this case, we couldn't find experimental data relevant to either broken and unbroken specimens at 10 to 7 cycles, but we could find only data relevant to broken specimens before 10 to 7 cycles. So we have only the red group of data points, which should lie all above the black line of the model if the correlation of the model with the experimental results was perfect. The correlation is not perfect. We have some data below the black line representing the model, but nevertheless the correlation is satisfactory. So in conclusion, we introduced a novel biparametric empirical model to estimate the threshold range of the stress intensity factor for long cracks of wrought and additively manufactured metals for different load ratios, namely -1, 0, and 0.5. The model is based on a microstructural length parameter and Vickers hardness, and has 4 coefficients which depend on the load ratio. The coefficients were calibrated with data from the literature. So the model allows to estimate rapidly the threshold range of the stress intensity factor for long cracks. The model estimates also the ideal defect-free material fatigue limit, and by using the model we could estimate the threshold range of defective additively manufactured materials with a satisfactory agreement with the experimental results. I thank you for your kind attention.